Okay, I think I'm gonna start in. I need to plug in my charger. Okay. I'll start at 7:05. Hopefully, someone will join by then. All right. Today, I think we have forced convection as the topic and without the questions. Let me share my screen. Okay, hopefully the screen is visible. All right, okay, I'll begin in 2 minutes. Okay, so let's begin. Um, Today we'll be discussing forced convection. It's better. Forced convection. Um, Usually in forced convection, as of now, I think today we'll be discussing forced convection over a flat plate. So I'm going to draw it in 2D. So let's say we have a plate like this. And afterwards, so we have some fluid entering. We have a fluid entering on top of this plate, which is somewhat like this. So it has a velocity, you can say u infinity. initially just before hitting the plate. And let's say this is a heated plate, okay? It has a temperature of Ts. Um, this edge is called trailing edge. Trailing. And this one is called the leading edge. So usually when air enters and it hits the plate, the velocity at the surface because of the no slip condition becomes zero. And gradually the velocity goes on. There's a velocity boundary layer which develops. So I'm going to draw that with the green pen, let's say. So this is how the velocity boundary layer looks like. And then there is a thermal boundary layer as well, which is usually of a similar nature, but let's as of now discuss the velocity boundary layer. So in all such cases, let's say if we want to calculate the velocity at this line, it is probably going to be somewhat like this. It's going to be almost zero near the plate. And what happens over here? How do we define this point? This is usually called, um, you can say, give me a sec. So usually, uh, we'll have to give some I mean, we'll have to explain somehow what is going to be the velocity at this point. So the way it is explained is when u becomes 0.99 times u infinity, that is the place where velocity boundary layer is formed. Velocity boundary layer is formed. So at this point, the velocity is u 0.99 times u infinity. At this point as well, at this point as well, at this point as well. Here it is going to be lower. Here lower. Here u infinity. But they had to define it somehow, so they just saw 0.99 because coming to exactly u infinity would be like a infinitely unresolved problem. So we cannot come to a good solution for that. That is why people chose 0.99 times u infinity. Now, I don't have, I thought I'm going to discuss more questions in this session rather than discussing the theory. So I think I'm just going to put up a few formulas. Um, so the shear stress tau s is defined as mu times dou u over dou y at y equals 0. By the way, this is the x-axis and this is the y-axis. So at y is equal to 0, what is the gradient of velocity times mu is the dynamic viscosity, and this is the shear stress. And why do we need the shear stress? Usually to define the local friction coefficient, which is CF. So CF at any point x is uh, tau s at point x over half times rho times u infinity squared. So these are the two formulas which usually are very commonly used in flow over a flat plate. They ask you to calculate the shear stress and the uh, local friction coefficient. Sometimes, majority of the times, then there is heat transfer coefficient as well. And usually they ask you to calculate the averages, and that's all. That's I think the majority of problems which I've seen on this topic are related to this. So what else do we have? Similarly, there is the temperature boundary layer as well. So let's maybe draw that using this pen. I'm going to draw it further on the top. So let this be the temperature boundary layer. How is this temperature boundary layer defined? So temperature boundary layer is defined as Ts minus T at any point x comma y over Ts minus T infinity is similarly very similar to the velocity case, 0.99 times. That's 0.99. So, and there is a delta T over here. So this is how the temperature boundary layer is defined. Now, what else do we have in the theory this time? Q convection. I think there is the concept of Reynolds number as well. We'll discuss that quickly. So the fluid velocity is usually quantized in terms of, it's usually represented in terms of Reynolds number. So at any point, Reynolds number at any x is defined as rho times u infinity times x over mu. And there is a critical Reynolds number above which the flow becomes turbulent. Before that is called the critical Reynolds number, and below the critical Reynolds number, the flow is laminar. Now there is a transition region as well, but usually we for the flat plate we just consider that it is a single point. So any point. So for a flat plate, um, Reynolds number which is critical is 5 times 10 to the power 5. What's next apart from this? Continuity equations. Then there are problems. Okay, I think that's all for the first review session on the forced convection. I'll quickly jump to the problems which I've shared with you guys um, in the Teams group which we have. So yes, I'll paste it here. Yes. This is the first problem which we have. Experimental results from the local heat transfer coefficient Hx for a flow over a flat plate with an extremely rough surface were found to fit the relation Hx then Ex is A times x raised to the power minus 0.1. So we have the local heat transfer coefficient H at any x, which is A times x raised to the power minus 0.1, where A is the coefficient and x is the distance from the leading edge. So very similar problem. This is the flat plate, and this is how the layers are there: thermal boundary layer and velocity boundary layer, and x is defined from here. So this is positive x. Now develop an expression for the ratio of average heat transfer coefficient for a plate of length x to the local heat transfer coefficient hx at any point x. Okay. So, okay, you guys can have like 1 minute probably to think over and ponder over this problem, and then we'll solve it together. Again, I don't have anyone. Never mind. In any case, I'm like very happy to teach, even if no one is there, because I saw that At least one person did ask a few questions and was going through the recordings in for one of the previous sessions. So even if it like helps one person, it's like very good for me. I'm happy with that. Okay, so let's begin. Uh, so the fluid is entering in with the velocity of u infinity, right? And this is the thermal boundary layer delta x as a function of x. Now they're asking us to first of all calculate what is the average heat transfer coefficient h x bar, right? So h x bar would be, and the plate's length is x meters. So it would be integration of hx as a function of x dx integrated over 0 to x and divided by x, right? This is how you average out the function. So hx bar would be integration 0 to x a times x raised to the power minus 0.1. So 1 over x. Now if we integrate, we are going to get x raised to the power minus 0.1, right? So mm, it will be a times x raised to the power 0.9 over 0.9. Um, and if you just calculate, I mean, this x cancels with this one, so x raised to the power minus 0.1, a is multiplied at 0.9. If we send to the numerator, finally we are going to get this expression. Hx bar is 1.11 a times x raised to the power minus 0.1. So this is the hx value. Very, very simple problem. Now we just don't have to calculate hx. We are being asked to calculate the ratio of average heat transfer coefficient h bar for the plate. So hx bar over h. So hx bar over hx is 1.11 times a times x raised to the power minus 0.1 over, what is hx? Hx is a times x raised to the power minus 0.1. So these terms cancel out and we get the ratio as 1.1. Very simple problem, and we have the solution here. And now if like in the part B, they are asking us to plot the variation of h, x and hx bar as a function of x. So it is an inverse relation. So we use a plot. Hmm. So let this be our h and let this be our x. So hx would be, let's say, somewhat like this. You'll have to think a bit about why I'm drawing it like this. It is because as x goes on increasing, the hx value goes on decreasing. Now, but hx bar is almost like 1.11 times hx. So that is probably going to give us something like this. These graphs are usually drawn qualitatively and not quantitatively because they just want to know whether you've understood the things properly or not. So, I mean, we could even quantify things like, for example, put x equal to 1 and then put some value of, okay, we don't even know a. So yeah, never mind. We could use an axis here which could have, let's say, a to a like this, and then probably we can do something. But like no need. Um, okay, I'll probably draw one marker here. Let's say this point is a. This is 0.5 a. So if we put x equals, let's say, if x is 1, then hx is also 1. So hx is a, right? So I think this point is what is going to be 1. At x equal to 1, we are going to get hx. So this bottom curve is of hx as a function of x, and this upward curve is of hx bar, right? Which is also a function of x. And then you can have multiple curves like this. So that's, I think, problem one is done. Let's jump to the next problem. Let's see. I have, I think, five problems this time. Okay, let's paste it here. Okay. The next problem. So this problem states that hmm, we have it here as well. So it's going to be easy. Okay. And vertical line here. It's okay. This problem says that in a flow over a surface, let's get this tiny bit. That's okay. So in a flow over a surface, velocity and the temperature profiles are of the form uy. Okay, I'll just write it down. U as a function. This is the velocity profile, which is ay plus vy square minus cy cubed. And the temperature profile as a function of y is d plus ey plus fy square minus gy cubed. So these are the two profiles which are given, where the coefficients a through g are constants. So a through g are all constants. Obtain the expressions for the friction coefficient and the convection coefficient h in terms of u infinity, t infinity, and other profile coefficients and fluid properties. Okay. Uh, I'm still going to spare like 1 minute for you guys to go through it. I mean, think about how to proceed with this problem, and then I'll solve it. Okay, so let's again draw the flat plate. So this is our flat plate, and let let me define this as the leading edge, and this is minus y, this is plus y, and that is plus x. Okay. So velocity profile is usually like this, right? This is how the velocity profile is. The temperature profile is opposite. So something like this. because the plate is hot and the surface atmosphere is cooler compared to the plate. This is velocity profile u as a function of x, and this is temperature as a function of x. Okay. So now there, first of all, we can get a few things very directly, as in let's do the math. So we are being given that. So what is the velocity at y equals 0 at this point? 0, right? So if we put y equal to 0 in this equation, are we getting 0? U as a function of y, ay plus by square minus cy cube. Yes, we are getting 0. So no info from that. That's like something which is quite evident. Now, there is one more thing. What is the, so let's say the temperature of the surface is Ts. So what is the temperature at y equals 0? It will be Ts, right? Because all along the plate, the temperature remains constant at Ts. This is steady state. So if we put y equal to 0 in the temperature equation, we must get Ts. So T as a function, T at y equals 0 is d plus 0 plus 0 minus 0, which is T. So T at 0 is Ts. So Ts is D. So we got one variable sorted. We got Ts, right? A through G we can use in the equations as well. So it's okay. Now next is they're asking us to calculate the friction coefficient. For the friction coefficient, what do we need? We need the shear stress, like we discussed previously. So shear stress, what's the formula for shear stress? Tau S is, what's that? U times dou U over dou Y at Y equal to 0, right? So very simply, tau S is mu times dou U over dou Y would be uh, A plus 2by minus 3cy square, if I haven't made a mistake in the differentiation, at y equal to 0, right? So this thing at y equal to 0. So tau s is going to be mu times a. That's it. Yes, this is our tau s. Now, what is friction coefficient? CF from this. CF is uh, tau s over half times rho times u infinity square. Can we use rho? Yes, because it says fluid properties we can use. Can we use u infinity? Yes. Can we use Ts? No, we have a better expression for that, which is mu times A. So what we are getting for CF is 2 times mu A over rho times u infinity square. This is the friction coefficient. So we got one part done. Coming to the second part of the problem. Uh, Obtain the convection coefficient H as well. So H is again very simple. H is defined as oh, I forgot to discuss this H equation previously. Never mind. You'll find this formula in the lecture slides. If hopefully, as I suggested, if you guys would have went through lecture slides before this session. If you didn't, then probably go back to the lecture slides and then come back. It's going to be much easier for you. I mean, everything is going to make sense after that. Anyways, the equation for H is minus K of the fluid times dou T over dou Y. Even I don't remember the expression, so I have it here. At Y equal to 0 over Ts minus T infinity. Um, Now, dou T over dou Y we can calculate, right? So let's first have that value. So dou T over dou Y at Y equals 0 is dou over dou Y time dou Y of D, is it D? Yes, D plus EY plus FY square minus GY cube at Y equals 0. So we'll get dou t over dou y at y equal to 0 as e plus 2fy minus 3gy square, all at y equal to 0. So we are going to get dou t over dou y at y equal to 0 as e. And that's it, right? Because these terms cancel out at y equals 0. So now if we use this and put this in, let's call this equation 2. Let's call this equation 1. So from 1 and 2, we'll get h as minus k of the fluid times e, which is dou t over dou y at y equal to 0 over ts minus t infinity. We got the heat transfer coefficient as well. That's all what this problem requires. Pretty straightforward problem. Okay, moving on to the next problem. 6.4. I've learned how to draw straight lines here. I have a little bit bigger. Yes. And a straight line vertically as well. Okay. Water at a temperature of 25 degrees Celsius flows over one of the surfaces of a steel wall whose temperature is 40 degrees Celsius. The wall is 0.35 meters thick and its other surface temperature is 100 degrees. Okay, one is 100 degrees, one is 40 degrees, and water is at 25 degrees. So the one which is near the water would be 40 degrees, and the other one is going to be 100. So, uh, I mean, that's how things are making sense in my mind. So let me draw it. Mm, okay. So we have a steel wall here. Okay. And above that, there is the fluid flowing. So draw the fluid like this. One more left, please. This is the fluid. And now bringing up the properties. So this is the steel wall. And what else have we got? The wall is 0.35 meters thick. So this is 0.35. And the T infinity is 25 degrees Celsius. And so this green color, this temperature is T is 2, which is 100 degrees Celsius. This temperature is T is 1, which is 40 degrees Celsius, right? Um, yes, okay. For the steady state conditions, what is the convection coefficient associated with the water flow? So you need H. One thing which they are asking for is H. H is what? And what is the temperature gradient in the ball and in the water that is in contact with the wall? Sketch the temperature distribution in the wall and in the adjoining water. Okay, a lot of things. Never mind. So we'll take a tiny surface here. So if you take this little surface here and do the energy balance from here, there is like energy inlet from here because the bottom surface is being maintained at 100 degrees, and there is E out. The fluid is taking away the energy, right? But this surface, due to being very, very tiny, is not able to hold any energy itself. I mean, the M is almost negligible, that's why. So we can say E in is equal to A out, right? So E in is almost, not almost, like practically we can say almost, but here exactly equal to E out. And what is E in? E in would be the uh, heat due to conduction, right? Conductive heat inside the steel wall would be equal to convective convection heat, which is being taken away by the fluid, by the water. Uh, and let's call this minus x, let's call this plus x, and this surface be origin. Okay. So there are a few properties which we are going to need. It's not there in this question itself, but we will be using in this problem. Usually in your examinations, if it's not open book, then those values will be given to you. If it's open book, you'll have to probably go to the end of the textbook and then look at the tables of thermal conductivities and find out the values of thermal conductivity of two things. Here it is steel wall AISI 1010. So I'm going to call it K steel. It is 61.7 watt per meter Kelvin. And K of H2O is 0.62 watt per meter Kelvin. Okay. So these two values you'll have to pull out from the appendix or from the problem itself if it's given. Now let's proceed to using this equation, right? Q dot conduction is Q dot convection. So what is the conduction heat transfer equation? What is the Q dot? It is K of steel. Please be careful here which K we have to use. This conduction which is happening in the steel wall, that is why we are using K steel times uh, what is the temperature difference Ts2 minus Ts1 over the length, which is let's call it L, okay, which is 0.35, is equal to the heat transfer coefficient times Ts1 minus T infinity, right? So from this we are going to get K K steel, which is 61.7 times 100 minus 40 over length is 0.35 is equal to H. We don't know H yet. H is what we have to calculate. Times Ts1 minus T infinity. Ts1 is 40 degrees, T infinity is 25. From this, it's pretty simple to calculate H. And the value which I have got is 705 watt per meter square Kelvin. You guys can calculate yourself and then please double check. If you don't get this value, you can ping me in the Teams group, but probably it's correct. Hopefully it's correct. Okay, so now H is done. What is the temperature gradient in the ball and in the water that is in contact with the ball? Okay, temperature gradient. Ah, okay. So it is dou T over dou X, right? But at the surface, at the intersection point of the steel and the fluid. So uh, they're asking temperature gradient in the wall. So dt over dx in the steel wall at x equal to 0 is question mark is what we have to calculate. And in water, it would be dt over dx in H2O x equal to 0. Okay, so dt over dx in the steel is very, very simple. It's 100 minus 40 over 0.35, right? Averaging out stuff, which is 171.4 Kelvin over meter. I can use degree Celsius over meter as well, but Kelvin over meter is also okay. So this is uh, the temperature gradient in the wall. Now in the water, what is it? dt over dx, what would it be? Uh, do you remember the formula for the heat transfer coefficient? H is, I mean, you can use minus H over K times PS1 minus P infinity here. And what K are we going to bring in here? This would be K steel, right? So this is for H2O. Okay, this is for H2O. So we have all the values, I guess. So dt over dx for H2O at the surface is minus times 705 over what is KST 61.7 times TS1, which is 40 degrees minus T infinity, which is 25. So here, because it is just the temperature difference, that's why we can take degrees Celsius as well as Kelvin values. But if you're solving a radiation problem, please be very, very careful. It's usually very, very misleading, and people end up using degree Celsius, and usually it's raised to the power 4, and it's a big mess. So always use Kelvin to be very, very safe. But if you are confident, you use degree Celsius. So the value which I have, the answer which I have is, how much is it? Okay, I have minus 17056 Kelvin over meter. This is for the water. Now, I think that's all right. Sketch the temperature distribution in the wall and the adjoining water. Okay, so for the sketching, I don't have the sketch with me right now. So I'll have to. So in the wall, it's pretty simple, right? In the wall, so let's use a blue pen for this. So in the wall, it's pretty straightforward. From here to here, from here to here, it's like a straight line. It is supposed to be a straight line because it is a linear relationship. Now, what is the temperature gradient here? After this, it is much higher, right? So the graph is going to get very steep like this after this. So this is how you can sketch the temperature distribution in the wall and the water. Uh, yes. So okay, the next problem is we have two problems left, I guess. Yes. Previously, I used to hold almost like 2 hour sessions at a stretch, but now I think because we are taking less time in theory, so I'll be able to wrap up things in like an hour. We've already spent like 46 minutes as of now. Still struggling a bit with drawing a straight line. Black pen and I paste my stuff here. This, this is the next problem. Um, so I don't want to move it anymore. Parallel flow of atmospheric air over a flat plate of length 3 meters is disrupted by an array of stationary rods placed in the flow path over the plate. Okay, can I just have copy this part and then I paste it here so it's little easier for us. This, this is good. So parallel flow of atmospheric air over a flat plate of length 3 meters is disrupted by an array of stationary rods placed in the flow path over the plate. Lab measurements of the local convection coefficient at the surface of the plate are made for the prescribed value of V and Ts, which is more than T infinity. So the plate is hotter and the atmosphere is cool. The results are correlated by an expression of the form Hx is zero point 0.7 plus 13.6 times x minus 3.4 x squared. So um, they have got an expression for hx already. So hx is 0.7. This they have determined experimentally. 13.6 times x minus 3.4 x squared. Everything is in SI units and evaluate the average convection coefficient HL bar for the entire plate and the ratio HL bar over it. I think pretty simple. Nothing at all. So we just have to calculate HL bar, which is 1 over L times integration of Hx as a function of x dx integrated over 0 to L, right? So HL bar is 1 over L times integration 0 to L 0.7 plus 13.6 x minus 3.4 x square times dx. This time recording this meeting locally on my PC so that there are no disruptions due to internet disconnectivity or whatever. So this is HL bar. HL bar would be 1 over L times 0.7 x plus 13.6 x square over 2 minus 3.4 x cube over 3 and value 0 to L, right? So HL bar would be 1 over L times 0.7 L plus 13.6 L square over 2 minus 3.4 L cube over 3 and the 0 terms will be 0. So HL bar would be finally, what is the value which I have got? Let me see. L is 3 meters, right? So we have everything. If you put L equal to 3 um, and L equal to 3, so we are going to get HL bar is 10.9 watt per meter square Kelvin. This is the value which I've got. Again, please cross check and let me know if it's incorrect. I made a mistake once in one of the previous recordings, so that's possible. So what is the, okay, so let's use a red pen. And what is the heat transfer coefficient over here? Can someone tell me? It's if x equal to 0 here, right? So from this equation, we can get the heat transfer coefficient at the leading edge is 0.7. They're asking us to evaluate the average convection coefficient HL that we have got for the entire plate and the ratio HL bar over HL at the trailing edge. Okay, so this is the trailing edge, right? Um, okay, so at the trailing edge, we are going to have HL bar over HL as a function of x at x equal to L would be 10.9 over 0.7 plus 13.6 times 3 minus 3.4 times 3 squared. And very luckily, in this case, this value turns out to be 1. This is very specific to this problem. This is nothing generalized. The equation which we had been given, the length of the plate which we had, because of all these parameters like matching out or cohesively working out nicely, we get the value as 1. It could have been anything. There's nothing special about this value 1. So, yep. And so actually, uh, if I were to draw this, let's, because it will be much more clear if I draw it once and then show you. Oh, so, so let's say this value is 0.7, okay, and this value is, let's say, 10.9, and this is x, this is h, so it's 10.9. And now, how is the HL bar going? HL bar is 10.9, right? At the leading edge. HL bar would be actually a function of x. In as a It would be a function of L, right? In this case, we had L equal to 3. But if x goes on increasing, then HL bar would turn out to be somewhat like this. Uh, and what would be the case of H HX, this thing? This would be having a maxima somewhere between these points. So this is x equal to 3, but we have 0.7 at the leading edge. So it's going to be somewhat like this. And you can even calculate the maximum value of hx, which would be differentiating it and equating it to 0, and then finding out the value of x at that point. That would be this value. And it will be between 0 and 3. Okay. This is not asked in this question, but I anyways thought I'll discuss. Now, I guess the last problem, and we are almost like at the 1 hour, end of 1 hour, which I had planned that I'm gonna like complete this session in 1 hour. So probably I'll be able to. Okay, I hope this problem is straightforward as well. I had pulled out these problems from the Incropera, and sometimes your textbook, I think it's Holman, right? Jack P. Holman. So uh, in the previous semester when I was taking this PTP, there were, I had to go through each of the problems and then choose which problem is most relevant and not that difficult, so that, it had to be a balance of difficulty and easy problems, because that's how you guys are going to learn. And I just thought I'll now discuss more problems and less of the theory, because problems are the ones which get your concepts clear. At least that's how things work for me. So now it's much easier for me because I don't have to pull out the textbook again and again and then search for problems and then look for solutions. Now I have the previous semester's problems which I chose, and then I just put up the same in the Teams chat which we have. Same goes with the professors as well. They have to create the slides for a new course once, and then same slides you will go on using again and again. Okay. For a laminar-free convection from a heated vertical surface, the local convection coefficient may be expressed as Hx. Okay, this is a heated vertical surface. Okay, I think I did not discuss a vertical surface. Let's see. By the way, I have shared a good resource with each one of you in the Teams group. It is a handbook which contains all the formulas for the heat transfer module, and it's pretty handy. Just if you have that, you can solve all the problems. Okay, so Hx is Cx raised to the power minus 1 over 4. Hx is the coefficient at a distance x from the leading edge of the surface, and quantity c, which depends on other fluid properties, are independent of x. Okay, c is a constant and x. Obtain an expression for hx bar over hx, where hx bar is the average coefficient of the leading edge. And this is just the vertical plate, but vertical plate has been discussed in the lectures, I guess. So we can solve this problem. I don't think it's a big issue. Anyways, it doesn't matter because we have been given the hx as a function of x, right? So nothing is like difficult here. So we just have to calculate hx bar, which is 1 over, we have the length of the plate, no, right? 1 over x times integration 0 to x, c times x raised to the power minus 1 over 4 dx. So hx bar would be 1 over x times c times x raised to the power 3 over 4 times 4 over 3, which is, so from this we are going to get hx bar as 4 over 3 c times x raised to the power 1 by 4, right? X raised to the power minus 1 by 4. Uh, and what else? Do we have something else in the problem? 4 over 3. Okay, so this is the hx bar. We have to calculate ratio of hx bar over hx bar to hx. So hx bar over hx would be 4 over 3 cx raised to the power minus 1 over 4 over c times x raised to the power minus 1 over 4. So I think these terms cancel out. We get 4 over 3 as the ratio we have been asked to calculate. And sketch the variation of hx and hx bar with x. So very similar to the first problem. I think it's exactly the same problem. So h is here and x is here, and it's an inverse relation, right? As x goes on increasing, the hx value decreases. So I I think I'll, no, I don't want it as a straight line. This would be hx, and on top of it, because it's 4 by 3, right? Hx bar over hx is 4 by 3, so on top of it and going slowly near the lower bound, this would be hx bar curve. So yeah, that's all. Um, that's it. Let's end it here. And it's exactly 1 hour, 1 minute. So thank you for bearing with me. I'll see you next week, probably.